All right, so I'm here with Professor Randy Skinner. He teaches geology here at BYU, and he's also the director of the Central Utah STEM Fair.
Yes, and we are doing a little interview, and I have a couple of questions, and I'm going to start with Alicia. And I would like for you to explain to me just a brief overview of your final project product.
So here is a middle phase model of our product. And what we did is we wanted to create a more realistic solution to refugee housing. And in order to do this, we realized we wanted to be transportable, lightweight, cheap, and wind resistant. And so the thing is, domes are the most wind resistant shape, right? So it had to be dome-like, but it also had to minimize the use of material. So when we looked around and we looked at different mathematical principles and conjectures, we found that the honeycomb conjecture, which basically explains that hexagons use the least amount of material but create the most amount of space, is by far the best shape to use because it minimizes the end cost. But hexagons tiled that are isoparametric alone only create a 2D plane.
So are you guys going around Utah County stealing stop signs for this now, or?
Those are octagons.
Hey, for some reason I thought they were hexagons. You can edit that part out too.
And, but we needed to add some curvature to this. So we found the law of phi. And the law of phi basically states that when I add a pentagon to a system of hexagons, it creates the correct curvature needed to create a dome or a sphere. The problem is pentagons use more material than hexagons. And so we needed to minimize the use of pentagons overall. And we found that when we add 4 pentagons in strategic locations around the dome-like structure, it still maximizes the use of hexagons, thus reducing the end cost, but still creates the curvature needed to create a dome-like sphere that's highly wind resistant. And so in total, when you calculate using corrugated plastic which is treated, it can last up to 18 or 20 years. Theoretically, we have proven that it can resist winds of over 100 miles per hour, and in total, it's 4 backpacks weighing 48 pounds. For a 5 to 6 person hunt.
Excellent. All right, so would you explain the engineering process that got you to here?
Yeah, so first we wanted to identify a solution to the problem of the refugees and the amount of them that were in the refugee camps. And so we decided that we wanted to build them houses for temporary because they don't know when they're going to be getting back into their homes or into different countries. So that was the problem that we found, is that they needed houses. And then we came up with a solution, which was using the laws of phi and the honeycomb conjecture to engineer this house. And it took a lot of process and a lot of redesigning and reevaluating our design and changing things until we got it to what it is today.
Now you said it's more wind resistant. You said it's more wind resistant. I remember you talking about how you did wind tunnel testing with this. How did that go?
So wind tunnel testing, last year we didn't have a lot of resources, so we needed to see what could we do that would be similar to like a wind tunnel. So we looked it up and we looked at resources that we had, and we created our own wind tunnel using an industrial-like fan, and we calculated how to create the rotational wind velocity using vega equals theta over time. And theoretically, we have proven that through the wind tunnel can resist winds of over 100 miles per hour.
What about external help, other resources that you had to make this work?
So we had a teacher or mentor, and we always say that he helped us by not helping us. Instead of giving us the answers to things, he would just say, well, go look up this or go Google this, and then that would lead us to find the answers on our own, so that way we understood the project better.
Oh, very nice. What was the catalyst that got you on this track? Why did you come up with this project?
Well, about a year and a half ago, we were thinking, well, we want to do a science fair project, but what could we do? And we were watching a TV show. It's called Henry A. Nation's Innovation Nation, and it was basically like a project for science kids. And they had an idea. It's called Cardboard Gami, and it's basically something like what we're doing now, but it's very expensive. It's a refugee housing solution, but it's $600 to $700, and only resists winds of over 30 miles per hour. And so we wanted to see what could we do better, and we love science and we love physics. So what could we do better? And that's what got us on this path.
Gotcha. Why is it that you love science so much?
Science is something that combines all great thoughts. It combines math, creates a map for history, uses English in its basic essence. But really, I found, even going to the international level, that a different perspective changes everything. And that's the essence of science.
Excellent.